Welcome everyone to our sixth summer presentations for Los Alamos Faith and Science Forum. Yeah, first we'd like to thank Chick Keller for dinner, and then we had...
and the other people who did the salads and the desserts. Well, it was a team effort.
Yes, it was. And Selma, who did the desserts, and Selma, who's actually provided desserts all summer for the forum, which is pretty amazing. But anyway, she's great. So tonight we'll have the second portion that is inspired by the book Is Earth Exceptional? And this one will be a journey through the cosmos in search of life. And we'll have two speakers tonight. We'll first have Chick Keller, and then Joyce Guzik will give the second part. So for Chick Keller entered Catholic seminary after high school. After 4 years of philosophy and theology, he realized that traditional theology needed to be updated by modern science. He studied physics and mathematics at Penn State and received a PhD in astronomy and astrophysics from Indiana University. After joining Los Alamos National Laboratory, Chick worked on a variety of computer-based studies, including climate change. He eventually became director of the Institute for Geophysics and Planetary Physics at Los Alamos. Chick was one of the founders of PEAK and is named one of the living treasures of Los Alamos. Chick has read widely about aspects of science as it impacts theology, and is a founding member of the Los Alamos Faith and Science Forum and has given numerous talks over the years. He is a member of Immaculate Heart of Mary Catholic Church. And for Joyce Guzik, is a laboratory fellow in the Applied Theoretical Physics X division at Los Alamos National Laboratory, where she has worked for over 35 years. Her research has spanned nuclear weapons science, global security, and astrophysics, including contributions to nuclear forensics and stellar evolution and pulsation modeling. She holds a BA in physics and math and Russian studies, and a PhD in astrophysics from Iowa State University. During the past 18 years, she has collaborated on projects using data from NASA's Keller and test spacecraft. So she's an expert in the area that she's presenting. And so these space missions have discovered thousands of planets orbiting other stars. A longtime member of Bethlehem Lutheran Church in Los Alamos, Guzik has engaged in adult theological education and has participated in programs exploring the intersection of faith and science. So let's thank Chick first, who will be our first speaker. Okay, thank you.
Get any after you speak. It's glad to see you all here. This book, I think, is very recent, and if anybody gets really interested and wants to read it, it's just a quick thing to Amazon, and the next day you'll have the book. But it really shows all the work that's been done to try to see how life could begin. And some of the constraints are such that they can actually predict what the Earth was like way back then. My talk today is pretty much going along the lines of the title, Is the Earth Special? One of the questions that everybody wonders about is, are there other people like us out there somewhere? And there's been a lot of effort done. For a long time, they weren't sure that stars had planets. Now we've come to the conclusion probably all stars have planets. And they keep finding more and more. There's a selection effect so that you find the big ones, because the little ones like the Earth are much harder to find. But Joyce will be talking about that. I'm just going to talk about why the Earth is special. Approximately 100 billion stars in our galaxy. Now I want you to not go to bed tonight until you've counted to 100 billion. You can count in tens. Shouldn't there be other examples? Most say yes, and optimistically say maybe, one for each galaxy. That's how rare it is. Let's look and see if that's a good estimate. Where the stars are, the planets that are going around stars, where the stars are is really important because stars interfere with each other if they're in big clusters and this and that. And what you need to have is stability. Imagine the stability of our planet. It's been going around the sun pretty much the same for 4 billion years. I mean, it has to be left alone. There can't be another star coming by, pulling it all out and doing things. So we're likely out in the boonies. How many stars then? Maybe a tenth of all the stars, maybe 100th, even 1,000th. If you look at the galaxy here, there's the center and these spiral arms, and we're right here, which is not in one of the spiral arms, but very close. So when you look out at the Milky Way, did you ever think about the fact that when you look at it, it's over there? If you were in the Milky Way, it would be everywhere. But instead, it's over there. That's why you see it that way. So we're in a very stable place. Now, Drake made tried to quantify the chances of having life. And he went through, and I'm not going to do this right now, but I'll do it a little later. He went through an equation and looked at what were the possibilities of this and that and the other thing. But he left a lot of things out. The first thing is the planet has to be at just the right distance from its star. Now, if a star is a cool dwarf, it can be pretty close. If it's a great big hot thing, it can be pretty far away. But it has to be in what we call the Goldilocks zone, which is right in here. Mars, for instance, is pretty far out and it's sort of cold. Venus is pretty in and it's pretty hot. And in finding planets, Joyce will be talking about how many planets we're finding that are in their Goldilocks zone. It turns out that Jupiter, years and years ago, was much closer to the sun, and it stabilized the planetary formation in close. So Jupiter had a big task to do and did it, and it stabilized the orbit now. Now, if you look out at all these planets and everything else, how many had a situation like that? Very unlikely. Now, in addition, we've come to the conclusion that the early Earth had two huge collisions with Mars-sized planets. The first one blew off an awful lot of the light elements, and those finally coalesced into our moon, and that turns out to be really important. The second one did the same thing. Most of the light elements went away, but all the heavy elements like uranium and iron increased. So the Earth has more uranium and iron than what was in the solar system, what they're called solar abundances. How much uranium and iron is in the sun? That should be about the same for everything. And it is, but not for the Earth. The Earth has more uranium, and that's terribly important. The iron helps make the Earth's magnetic field. Without the magnetic field, a lot of the solar wind coming out from the sun would wipe out the Earth pretty easily. And so the magnetic field's important. The uranium decays and heats up the interior, and we'll talk about that. So here's a computer simulation of one planet running into another one. But the moon saves us. It does two things. The Earth spins on its axis, and we sort of think that's up and down, and as it goes around, it tips a little bit, but it pretty much is just tipped a little bit on its axis. What would happen if its axis tipped over so it was pointing right at the sun? Well, it would be all hot on one side and all cold on the other. Or if it tipped over even partially, that would be true to a large extent. The moon keeps that from happening. The other thing is, both Mercury and Venus have been affected by the sun's gravity so that they don't rotate very much. Mercury doesn't rotate at all, just once as it goes around like our moon. So our Earth has slowed the moon down so it has always one face on us. And so the moon keeps the sun from capturing the Earth's rotation. The moon interacts with the Earth and keeps that rotation at a reasonable amount. Now the rotation, of course, is important because if it was very, very fast, you'd have huge hurricanes and huge tornadoes and everything else. If it's very, very slow, it would get too hot in the daytime and too cold at night. So the length of the rotation is important. How special is our planet? Well, we just mentioned the rotation rate and the tilt. Now I want to talk about plate tectonics and some other things. But here are some things to think about. The magnetic field from a liquid iron core protects us from solar flares. The chemical makeup of the surface elements, there's lots of carbon, and so we're carbon-based. The atmosphere, we have to worry about its pressure and about its constituents. So we talked about this a little bit. What influences the rotation rate? It seems too early to be very rapid like Jupiter, and collisions could have slowed it down. Now, no matter how I tried to make this graph easy to see, it didn't work out very carefully. But supposing you have an ocean Earth, an ocean planet, and this land and that. Well, you know what happens? It rains and storms and everything flows down to the ocean. And all the mountains wear down. And if there isn't something to push them back up, it'll just be an ocean planet. And you can have life, but this won't be life that builds 747s and it comes to talks like this, because there won't be any land above the sea. So what happens? Well, what happens is because of all this heat, this uranium inside, the inside of the Earth boils just like a pot of water. The only difference is a pot of water takes a few seconds to boil. The Earth takes 100 million years to boil, but it's doing the same thing. And as it boils, it pushes things up and it pulls things down. And so the plates, the hard rock plates on the top of the Earth move around. And when they run into each other, like, no matter how you push it, when they run into each other, some of them go down, and the other ones are just sitting there. And when they go down, they push this up. And for instance, a lot of places where you see mountain chains, the Andes, for example, there's a plate from the Pacific that's going under South America and pushing up the Andes. The Alps, Italy is pushing into the European plate and pushing up the Alps. The biggest one is where India came floating north and ran into India, India came floating north and ran into Asia, and that's how we got Mount Everest. And so we're very lucky that we have extra uranium to make the planet boil, or we wouldn't have those plate tectonics. We look at other planets and we don't see that very often, if at all. So here's another special thing that the Earth has. Now, this is an interesting story. When I first came to the lab, you could talk to all these geophysicists and they would tell you why the Earth had its magnetic field. And then you'd ask them, how come every now and then it reverses and north goes from, and they didn't know. I told people, you ask a geophysicist that, and you know what they say? Gobble, 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 gobble. They didn't know. But here at the lab, we had a guy who was running very large computers of three-dimensional Earth models. And he called me up one Saturday evening, and I said, Gary, what's up? He said, the field just reversed. He was following all the motions, especially in the Earth's interior. Now, this is motions on an Earth that's spinning, so it's a funny looking thing. But every now and then, those things line up in such a way that the magnetic field reverses. 100,000 years or so it does it. These geophysicists didn't know that until Gary ran those models and showed that the uranium heating and the molten iron made the magnetic field. And that's another thing very special. Now, the atmosphere is special too. It's 80% nitrogen, so you're breathing almost all nitrogen. Lucky for you, nitrogen doesn't interact very much with carbon, and so it's just a thing you're breathing. But it's really good because it's a key building block for amino acids and for proteins and for life, and it's a great fertilizer. So it's nice to have that nitrogen around. But what happened years and years ago, the Earth just had nitrogen and carbon. There wasn't any oxygen. And life got started, and these little microbes turned out they had a byproduct. They made oxygen. And over 100 million years, the Earth's atmosphere switched to where it had this much oxygen, about 19%. Now, why doesn't it get more? If oxygen went to 25%, all the forests would burn down. It'd be really easy for fires to burn. If oxygen goes to 15%, all kinds of things, you don't get photosynthesis and this and that. And so oxygen sort of stays there at 19%. And so that's a very special thing. How many planets do you think would likely have this mix of chemicals in the atmosphere? Now, if the atmosphere is very big, the pressure at the bottom of the atmosphere would be enormous. That's the way it is in Venus. If the atmosphere is not so big, the pressure is hardly there at all, as on Mars. So we just happen to be in a planet which the atmosphere is just about the right size so that we get clouds and rain and get all kinds of things like that. Another special effect. Now, it says here, and Joyce will be talking about this, no matter what I push, it always goes the other way. Studies are pessimistic that discovered exoplanets will have an atmosphere like ours. Well, they haven't gone far enough along, and Joyce will be talking about that. The James Webb Telescope is detecting planetary atmospheres, so stay tuned. How do we think evolution proceeds? Well, Darwin's theory says that evolution has no direction. It's just random. So intelligent life might be quite rare. Most recent research seems to be showing that evolution is partially directed, and that's very important. What's the possibility that evolution is set up in such a way that it will always lead to intelligent people like you and I? The Earth has tried 5 times to do that. South America, no intelligent people. North America, no intelligent people. Africa, yes. Africa did it. Asia, no. Australia, no. So even though all these things are right, we only got 1 out of 5. Well, you could say, well, that was just the first one, and then we didn't need to go do any other ones. They would have come along. And so that's one of the things people will be asking. Okay, do you want to play Sim Earth? Everybody likes to play these games. So what about the Earth's size? If the gravity on Earth was twice what it is now, there would be no birds. And all kinds of other things. Animals would have big stocky legs, all kinds of things. Be a very, very strange place, and probably not very hospitable. That's the gravity. The axis tilt we've talked about, it stays pretty much up and down because the moon won't let it do anything else. Speed of rotation is just lucky. It's just lucky that it's what it is. Now, we have enough water from the oceans to cause a greenhouse effect. If we didn't have water, which is a greenhouse gas, heating our planet, the average temperature of the planet would be well below freezing at the distance from the sun that we are. And so the water vapor is our friend. It does most of the warming. The carbon does a little, and unfortunately we're putting more carbon in, so it's going to do even more. And that will cause the oceans to evaporate more, and that'll be another greenhouse back. So it's a feedback loop that's going to get worse. We have more uranium and iron, large close moves, special conditions for starting living things. Calamities like the Permian dying, that was a time, millions of years ago when something happened and almost everything died. And of course, when the meteor hit the earth and killed all the dinosaurs, most everything died too. And so we have to have very special conditions to evolve intelligence. So if you want to play Sim Earth, you pick what you want for each. Pick a size, pick a gravity, pick a tilt, pick all those things and see if you can make a different Earth that would produce intelligent life. Fermi's question, it was the old cafeteria where he and Stan Ulam and in my old age, I can't say it, I'll think of it in a minute. Two scientists, really good scientists, were sitting there with Fermi and they were talking about the possibility of life in other places. And Fermi didn't say anything. And they finally said, well, Enrico, what do you think? He said, where are they? Everything is billions of years old. If there was a bunch of living people out there that were 1,000 years younger than us, or older than us, they'd be here. So now you can say, well, they're here, but they know how to remain invisible, so we don't see them. Some of the people you see, you might wonder if those are them. And so there's a whole thing about UFOs. And a friend of mine really liked it. The guy said it was a positively identified UFO, unidentified flying object. Positively identified, unidentified. Okay, I decided to do the equation myself with these kinds of things. And you can put these numbers in yourself if you do Sim Earth. We're figuring 1/10 of the stars are in the right place, and a lot of the stars don't last long enough, so it's only the stars like the sun and cooler stars that last long enough to have this happen. But there's a lot of them, so I said just 1/10. Binary stars, one star would mess up another star, and now there are some binary stars that are so far apart they wouldn't affect each other too much, but most of them they would. Planets, well, number one, we're figuring that all stars have planets. Planets in the Goldilocks zone, well, if you count, Joyce will give you a number for observationally how many we have observed to be in the Goldilocks zone. I'm saying 1%. But how about a collision that makes a large moon that stays around the Earth and stabilizes it? That's pretty rare. So 1/10%. Enriched uranium, well, you had to have another collision, so it's another only 1%. Right size atmosphere, 10%. Enough water, 10%. Right rotation, 10%. Right mass, 10%. Life, 0.5%. So you might get life, but maybe not. Intelligent life, far less. If you multiply all those together, you get this number, 3 times 10 to the minus 14th. Not a very likely thing. If you look at all the stars in our galaxy, 2 times 10 to the 11th, you can see that leaves us with at least a less than 1% chance to have even us in the galaxy. So you can do that and argue with those numbers and put in different numbers and see if you can pump that up and get it so that there's 100 planets in the galaxy and this and that. But it's worth trying to do that. Now, I want to point something out to you. This is a question for you. How many stars, individual stars, are in this picture? 3. This one has, when they have those lines on them, that's because they're bright enough. So there are 3. Everything else you see is a galaxy. So even if there's only one intelligent life in a galaxy, there's a billion intelligent life. Even if there's only one. Look at the number of stars. We didn't know this till the Hubble found this out, and now the Webb is showing it too. Look at all those galaxies, all the way down to those really tiny fine things. None of those are stars. They're all clusters of stars, galaxies. This talk assumed that life must be carbon-based. I think that's a pretty good assumption when you look at the chemistry of things. Carbon is one of these things that has, it can get 4 electrons or it can give 4 away. And so it can take many, many forms. So carbon is the thing from which you could get all these different molecules and things you need for life. And there isn't any other one that might do that. Earth-like planets are probably rare, we're assuming that. The evolution might be strongly directed to intelligence. It might, as I said, on Earth there was 5 attempts and only 1 made it. There are a few places in the galaxy hospitable to stable planets for billions of years. So you have to be out in the boonies. So we've made those assumptions. So what about faith? So our faith must be slightly modified. Before these scientific findings, it was thought that the Earth was the only habitable planet and that it was specially created by God, and there was only one true religion. And we have for years run around knocking on the heads people who thought they had the one true religion because we had the one true religion. And as the Inquisitor would say, wrong has no rights. And so if you're right, anything you do to people who is wrong is good. It's godly, you see. So you can kill them. You can do anything to them. The only trouble is the other side saying the same thing. But we all agree, as in Psalm 66, say to God, how tremendous are your deeds. And several questions must come up. But the one that I think is the most compelling question is, why would God do this? He made billions of galaxies for us? I'm out of time, aren't I? Yeah, well, I'm almost done. And so when you're sitting and don't have anything else to do, try to make up a reason why God would make 13 billion years till it gets to humans and have all these billions of galaxies. Even if there's only one Earth-like planet, there's a million. But it's always, how did that happen? Well, I'll just finish. In your discussion group, there'll be some questions about that. But one of the conclusions you come to is that there isn't one true religion. There are billions of true religions. None of them are perfect, but they're, like us, getting close to being perfect. And they're based on the cultures of those different people. Now, the only trouble with that is you can look at our Earth and you see Islam, you see the Hindus, you see Jewish people, you see other religions. Most of them want the same thing. They want a good life. They want you to love your neighbor. They want you to, do good to other people. So they all have essentially the same goal, but they do it based on their own cultures in which they're comfortable. And so you might come to the conclusion that ours, Christianity, isn't the one true religion. It's just one of the true religions. Now, if you look at the Psalms will tell you that all nations will come to God. Well, we haven't seen that happen, and you can say, well, we'll wait a little longer, but it's been a pretty long time. But if each one of these religions is responding to God, that psalm is correct. Thanks very much.
Oh, just a second. We'll have questions. So, questions or no. We'll go ahead with Joyce's first. So, I've had a number of comments. We received a number of comments about that these presentations are very science-based. There's not a lot of faith, and Chick has introduced a bit of faith into it. So, we kind of wanted to structure it so that most of it was science, and then at our table discussions, as questions at the tables are more faith-based. So we'll move to those questions and cover that area as well. So thank you.
Would you rather have Chick answer questions now?
No, let's go ahead with your presentation.
Okay, do I need... Okay. So I am basing my talk quite heavily on this book that the title of our presentations is called Is Earth Exceptional by Mario Livio and Jack Sostak. And last week you heard Becky Chamberlain, who was a student at one point of Jack Sostak, talk about the biochemistry part. So I'm going to be talking about some of the back half of this book, the star part. Click on, it goes down there, okay. Yes. Okay, wonderful, thank you. Okay, so this is an outline of my talk. I'll see if I have enough time to finish all of this. I'm going to talk about the search for planets, extrasolar planets, searches for planets outside of our solar system. I'm going to talk about which kinds of stars and planets could host life. How would we go about detecting life? What have we found so far? And then how would we detect intelligent life? And what have we tried so far? And we can speculate on the question, are we alone? So an extrasolar planet, often called an exoplanet in the news and science, the first planets around stars outside of our sun, the first one was actually discovered very late, 1992, and it was discovered around a pulsar, a neutron star. So of course that planet orbiting a neutron star is not going to be very hospitable to life today. So, when most of us were born, we knew of no planets around stars outside of our sun. And in 1995, the first star was found that had a planet around it, and it was a sun-like star, and that's 51 Peg B. And as of June 26th, if I look on Google, it says that there are 5,926 confirmed planets. So that's a big change from a few decades ago. And based on statistics of a way of discovering planets called planetary transits, we believe now that most stars have at least one planet, and many of them have more than one planet. So how have planets been detected? Well, there's several methods. I'm going to focus mostly on this first method of transits, and there are about 4,500 that have been discovered that way. That's about 3/4 of the planets outside of our solar system. We'd also discovered them by radial velocity, which is where you take a spectrum and you see the star looks like it's coming towards you and away from you, which means that it has something orbiting it. So it's moving, wobbling back and forth, and you can deduce how big that object is and that it must be a planet from that motion. Another way is just direct imaging. If this planet is close to us and our telescopes have gotten better, we can actually see the planet next to the star. Gravitational lensing is another way we've discovered planets. Astrometry, which is again measuring the position of a star. If we see it moving around, we know there's something else orbiting it that we can't see, so that's probably a planet, and a few other methods. But the transits are the most important. I don't know if anyone in this room has seen a planet transit in our solar system. Has anyone seen the Mercury transit? Okay. And the Venus transit? Yes, all right, great. So you know what that is. So we discovered planets around other stars using the same method. Now, we don't see the Mercury transit very often because our Earth is in a slightly different plane than Mercury or Venus. So we have to be lined up just right to see it go in front of the sun, and that doesn't happen very often. But there's me in White Rock in 2019 on Veterans Day. I could stay home and watch the Mercury transit, and you can see that little dot Up there, that's our picture, and something from the web. So you see Mercury just goes across over the course of an hour or so, but it actually only blocks a tiny, tiny fraction of the light, 0.0012%. So you really need very accurate photometry to see that kind of event on another star. So this, and the next one, by the way, is in 2032. So hopefully many of us will be still alive to see the next Mercury transit. So we won't be so lucky with the Venus transit. The next one is 2117, and I'm not going to make it that long. Maybe some of you will. So this one happened in 2012 in the summer. So there's me at UNMLA projecting the sun on a piece of cardboard. And you can see Venus is quite a bit bigger planet than Mercury, so it subtends more of the sun. It went across there in a couple of hours. And it blocks more, but still only 0.0076% of the light. So this is how those 5,000 plus and more planets have been detected around other stars. So the problem is it's easier to detect a big planet going around a small star than it is to get a small planet like the Earth, like we want to find where we could live, around a big star. As you saw, it's a very, very small thing. So if you have very, very sensitive photometers, you might get a tiny little dip like we saw on the left there when this Earth-like planet goes past the Sun-like star in another kind of star. But for an M dwarf, which is a smaller, redder star, that planet's bigger, and it's also for an Earth-like planet in the habitable zone, closer, so it ends up subtending more of the star. So you get a bigger signal. So most of the planets we found that are like the Earth or smaller planets have been around M dwarf stars. So one of the projects that found most of these stars was the NASA Keller mission. It was launched in 2009, and I was involved in studying the stars that were looked at by this mission. So it was pointing toward one of those spiral arms away from ours that Chick was showing in the galaxy plot. So we tried to look with Kepler near a spiral arm, but not in too dense of a region. And that little square with the 21 squares there of sky, it looked at that part of the sky for 4 years, hoping to catch a planet going by. If it's a 1-year orbit, it can take 1 year to go by, right? And you actually want to see it go by a few times to confirm that it's really a planet and it's not just a problem with your photometry. So they found quite a few planets that way, 2,700 confirmed now. But most of these planets and stars were quite far away. They were in that nearby spiral arm, 1,000 light years or so away, 2,000 light years away. So it wasn't as exciting, and we really only found a couple planets that were as small as the Earth with that mission. And then we launched another one 10 years later, the Transiting Exoplanet Survey Satellite, or TESS. And this satellite is in a lunar resonance orbit around the Earth, and it goes by the moon and gets a little bump to keep it in orbit every 13.7 days, so about 27-day time, or twice that. It stays looking at the same strip of sky, one of these blue strips. So it's looking at a lot of the sky, but only for 27 days. So these planets have to be going around pretty, you're not going to catch. If the year was a year long, you would miss that planet if you're just looking for 27 days. But with statistics, you can get quite a few. So far, they've found 638 confirmed planets and many, many more candidates that they need to follow up with to see if they can verify it some other way. So this was looking mostly at nearby stars. So which kinds of stars could host life? And Chick did a good job arguing that a star like our sun with a planet like our Earth is very unusual because all these things have to happen. But astronomers aren't that pessimistic, I guess. They're mostly looking in the habitable zone, or the Goldilocks zone, defined as a place where liquid water could exist somewhere on the planet. The temperature gets to the point where you could get liquid water. And the planet and the star have to live long enough that not just life forms, but if we want to see it, know it's there, it has to be detectable. And on our Earth, it took a couple billion years for bacteria and things to build up to make the oxygen in our atmosphere so that we could, if we were looking at it from the Hubble or the James Webb Space Telescope today, we could see that oxygen. So the star has to be fairly low mass, less than 1.5 times the mass of the sun, or it would not live 2 billion years. It would burn all its hydrogen into helium in the core. It would evolve into a red giant and supernova if it's big enough, and so there's not enough time for life to develop. So less than 1.5 solar masses. And so we tend to look, especially with the other thing is that the lower mass stars are much more numerous. 70% of stars are these redder stars called the M dwarfs. And because they're more numerous, most of the stars nearby us are red dwarfs. And those can live trillions of years. So that's a good place maybe to look for life. And we estimate that 80% of M dwarfs have planets in the habitable zone. But there are pluses and minuses for M dwarf stars. One of them is they're very active, they have big sunspots. So you see this light curve for an M dwarf from Keller, it's going up and down and up and down. That's a big sunspot going around the star, making it brighter and dimmer. And then you see these things every few days, 10 days or so here on this particular M dwarf, these big spikes. These are flares, so lots of ultraviolet getting shot at the planet. And your planet in the habitable zone is very close to the star. It takes like 10 days for that planet to go around the star. It's really close. So it's going to get blasted by those flares. The other problem is because it's close to the star, it's probably tidally locked. It has the same face toward the star as it's going around, like our moon is doing with the Earth, same face. So it's going to get cooked on one side and frozen on the other. So why is this a good place for life? So a lot of people think we're just looking in the wrong place. We're looking at these because it's easy. They're nearby. We can find them. We can see a planet around a small star easier than a tiny planet around a big star. But on the other hand, this book is not that pessimistic. There may be a magnetic field on the planet, like on our Earth, that could provide shielding from the solar wind, from the stellar wind, and from the flare activity. And atmospheric circulation. If you have an atmosphere on the planet, even if it's tidally locked, you might get a hot and cold. So heat or winds could flow from one part of the planet to the other, and maybe give you a place where life could exist. So this was a little bit more in Becky Chamberlain's wheelhouse last week, but the James Webb Space Telescope is starting to look at these nearby planets and look at their atmospheres and see if they can find evidence of life. So things like oxygen with water vapor and methane, some kind of disequilibrium. If you have several gases together that couldn't exist together unless life was replenishing one of them, because it would be reacting or leaving, that could be evidence that life is on that planet. One of the planets I'm going to talk about detected maybe dimethyl sulfide, which is made on the Earth from plants and bacteria. So that could be an indicator that there's life on that planet. Other things, looking for evidence of oceans, looking at the chirality of amino acids, if they're all one-handedness, left or right, that could mean that that's life and not just random molecules. Time variations on the planet like seasons, and really to be sure you'd want to find several indicators at once. And this book says that we are either on the verge of discovering extrasolar life or will soon be able to place meaningful constraints. And I think that's going to happen in our lifetimes, within the next decade or so. So I'm just going to show you a few pictures of some artists' renditions of planets that have been looked at to try to see if they could have life on them. And this is one of the ones I was talking about, K218b, and this is the one where they think they've detected dimethyl sulfide in the atmosphere. It hasn't been confirmed. There's papers going back and forth on whether it's really there. And it's produced on Earth by life, but is there another way to produce it? That's something you have to prove, that it can't be made any other way to really know that this is a planet that has life on it. Its surface gravity is 1.2 times Earth, so you'd be a little bit heavier on this planet. Most likely it's tidally locked. It's 120 light years from the Earth, so not very close. Here's another pair of planets, TOI 700d and E. They're 100 light years away. One of them receives 88% as much sunlight, and the other planet that's further in is 127% as much sunlight as the Earth. Their days are about a month long. Surface gravity is high on one, low on the other, so our Earth is kind of in the middle on these two. Doesn't match up with either one. Fortunately for this planet, the M dwarf has low activity. There aren't that many flares, so that's a good thing. It may actually help. This system is really interesting, TRAPPIST-1. It has 7 planets, and you can see them lined up to scale against Mercury, Venus, Earth, and Mars in this artist's drawing here. And we think that D, E, F, and G may be in the habitable zone. This is a little bit closer, 41 light years from the Earth. Looking at the star and various things like its metallicity and its motion around the galaxy, we think it's 5 to 10 billion years old, so plenty old enough for life to have formed. So we're looking pretty hard at this one. So far, they haven't found any atmospheres around these planets, though. And this star is one of my favorites. You know about Alpha Centauri? It's one of the nearest stars. It's four light years away. We could send a signal and get it back in less than a decade if there was someone to answer. So it orbits an M dwarf star. The planet on Proxima Centauri here is 1.07 Earth gravity, so very much like the Earth's. It's quite a bit colder on the average temperature, though, 38 below zero, and it orbits very close to the star with an 11.3 day year. But it also has, as we found in May 2016, giant flare. So what are our prospects? Well, they quote Sarah Seeger, who works with the TESS and the JWST data, and Sarah says, based on her equation, looking at all the prospects, that there's only a 0.036 chance of detecting life on an exoplanet using the TESS data plus the James Webb Space Telescope looking at the atmosphere. I don't know if I am that pessimistic, but that's what Sarah estimates. And in 2020, astronomers got together, they do this every 10 years, and propose what the next generation of space missions should be. And they proposed wanting to do this Habitable Worlds Observatory, the follow-on space telescope with a giant mirror instrumented all over infrared optical UV coronagraph, and they want to directly image 25 planets that they've decided are good candidates from the TESS and JWST work, and use spectroscopy to characterize the atmosphere. Now, this is expected to be launched in 2040, 2045 or so, but you know how these things get delayed and delayed. I don't think this is going to happen anytime soon, and with the budget cuts in NASA right now, it's hard to say. So I'm going to move on quickly to talk about intelligent life. This is getting maybe more speculative. So to find intelligent life, you need to see technology. You need to maybe see some astroengineering project going around a planet, maybe a civilization that's harvesting energy from its nearby star, generating a lot of heat, a lot of energy consumption and infrared going out, maybe seeing them control weather. And one of the big questions that Chick kind of mentioned is, how long does it last? How long will an intelligent civilization last for us to see it? Will it only be around for a few centuries or a few thousand years? We don't know the answer to that question. So there was one star that was looked at by Kepler that was in the news called Tabby's star. And they found these dips in the light curve just kind of randomly. And those could be, they're still trying to explain them. They think it's probably a dust ring or asteroid debris around the planet, around the star that's blocking its light. But someone suggested it could be a Dyson sphere, which is a sort of a science fiction-y thing where a civilization has put up strips of kind of solar panels around their star to gather lots of energy because they need it to power their civilization, their advanced technology. So searches for intelligence, you probably heard about SETI, the search for extraterrestrial intelligence using radio wavelengths, trying to see if we can hear someone trying to send a signal to us. Optical searches have been done at laser wavelengths. We could look in the infrared for this excess heat waste. And we can also look for visitors like UFOs from outside the solar system. There is an asteroid that came from outside the solar system called Oumuamua. You probably heard about it. And there's a scientist named Avi Loeb, and he started this project called Galileo to try to look for more of these. And they speculate that what if these are actually artifacts of an alien civilization that are passing through? Could we diagnose one of these objects and see if it has unusual metals in it or some kind of signature that it came from another civilization? And there's a new one coming by. It was discovered just July 2nd, and it'll be here in October. So Chick touched on the Drake equation, and in this book, they are more optimistic. They go through the terms in the Drake equation. We actually kind of know better the first and second now in our lifetimes than we knew before, the star formation rate and the fraction of stars that have planets, which we think is about 1, and fraction of planets that could allow life. Well, they're more optimistic than Chick was and think it's more like 20%. So, and one of the big uncertainties is how long will civilization release a detectable signal? It could be 1,000 years, could be 100 million years. And they estimate with their wide swings that there could be 20 civilizations in our galaxy or up to 2 million. So that's a lot. It says Earth is not quite unique. Our civilization, intelligent life, is not quite unique in our galaxy. So another possibility about why we haven't found these yet, are we looking in the wrong place? Have civilizations evolved into a post-biological artificial intelligence? And I wouldn't have thought about that much 10 years ago, but this book is hinting that they think it's almost certain we're going to develop AI and it's going to take over our consciousness, and you won't need biological life anymore. It can all be artificial. Do civilizations require large energy sources? Well, it seems like AI is requiring large energy sources. We're building more and more power for the data centers to keep doing AI. And if that's true, we might want to look at uninhabitable places, because they don't need to be in a place where you've got liquid water. They could be around a massive hot star that's giving them lots of energy, or around a black hole. And the other possibility is, are they deliberately hiding? I don't know if any of you have read this book, The Three-Body Problem, or The Dark Forest. It's really kind of a scary book, but the premise is that there is limited resources in the galaxy, and that if other civilizations find out about you, their best bet is to go destroy you so they can keep the resources for themselves. So you want to hide so they don't know you're there. That's kind of what I got out of that book. Okay, so where are they? This is, again, this book saying they think it's too pessimistic that we are alone, or that life is short, that they think that that's too anthropocentric. They think that we will solve our problems. If asteroids are going to hit us, we'll solve our problem with nuclear war and avoid it. We'll solve our climate problems. We'll last a lot longer than the pessimistic viewpoint. Another possibility, they've been here, or they're here now. They've already been here. They've planted life on the Earth. And another one, which I really hate, it keeps coming up, is the Matrix. You know, we're in a simulated reality from an alien civilization. I just don't believe that at all. And the last one is they exist, but we haven't detected them. And I think that's the most likely of these, actually. So we've got our discussion questions on the table. I'm ending right here. Okay, thank you. Should we bring Chick back up so we could get questions for Chick or me?
No, it's probably with waiting this long, as you probably all forgot the questions you wanted to ask. Go ahead, Nels.
I think Jack Shostak is funded. I think Jack Shostak is funded to do his research to investigate the possibility of life elsewhere. It would not serve his purpose to come up with a pessimistic conclusion. So do you think he's the most objective kind of guy to make an estimate of the probability of life?
Well, if you play Sim Earth, as I showed you, you'll have to come up with your own ideas. But I think the way they were doing it didn't include all the concerns that I had. Other questions? Yeah.
You spoke about the importance of the moon in our ability to have life on Earth. How vulnerable is the moon to being displaced in its orbit with us by, a collision of some type, or how strongly are we reliant on the position of the moon?
Those are things you can worry about, but the moon's been doing that for 4 billion years, so I don't think there's anything that's going to change what it's doing. I think it's pretty stable. Now, in the orbit is changing a little bit, but very slowly.
So not meteorites or asteroids or anything to... Okay.
No.
Thank you.
Good questions. Others? Yeah, back there.
You were talking about the tectonic plates?
Yeah.
And the motion of the rising and depression of the land masses. If there wasn't any tectonics, and so it was a smooth surface, relatively speaking, under the oceans, and the oceans covered everything, do you have any idea or estimate of how deep that ocean would be on average?
I think that that's an interesting question, because the land would be worn down just to the water, and so there would be shallow places and deep places.
Yeah.
So I think it'd be pretty much the same as it is now. It just wouldn't have anything above the water. So it could, as I say, it could make life, but it wouldn't be life as we know it.
Okay. So yeah, it's a few. So I guess we'll go ahead into our discussion groups and.
Any questions for me?
Oh yeah. Oh, I'm sorry.
Sorry, it's okay. You could have asked
I thought it
either one
was
of us.
general questions.
There's one.
Joyce, is there any possibility of looking for volcanic activity on the exoplanets or something like that?
I guess I don't see why not. We see volcanic activity on planets in our solar system, and they're, if they erupt and have gases that we can detect, and they come and go over years, I would think we could correlate that with volcanoes. Sure. Yeah.
So okay. One thing that Chick alluded to was that the atmosphere has changed over billions of years here. Basically, it started out being we would never be able to live in the atmosphere that was here when life first formed. It had cyanide gas, H2S, all these materials, CO2, and no oxygen. And then whenever life came about, plant life came about, there was basically a explosion of oxygen that occurred at that time and has existed ever since. That's allowed intelligent life. So you'd have to be able to look at atmospheres on other planets, taking that into account.
Thank you. It seems to me like SETI is probably the most attractive way of finding intelligent life. Have they ever found anything, or how far out do they clear the space?
Yeah, I don't know how far out they've cleared it, but I guess you can't detect a signal more than if it's 13.7 billion light years away, right? Because that's the age of the universe. But they go through a few false detections in here. They've detected some signal, and then they've had to figure out what it is. You can raise some radio interference or something else. So far, there's no definitive signal from SETI.
I thought it's pretty interesting that one of this around one of the stars that you're looking at was Vega, and that was a star around where contact was placed to near the nearest alien civilization. But anyway.
Yeah, so this might be either for Chick or Joyce. On the amount of uranium that the Earth has, that's the first I thought about that how important that is to have in our. So is that all? Since the heavy elements were formed after supernova and generations of stars, is that all considered? Is Earth have too much uranium? Compared to our theories of galaxy formation and how much uranium should have been there in the early days when Earth was formed.
I'm going to let Chick answer that question.
And the answer is yes. What you do if you look at the solar system is you look at the abundance of the different elements in the sun, and you write down that. And then when you look at other planets, to the best of your knowledge, you find pretty much the same thing. It's called the solar abundances. If you look at the moon, you don't have solar abundances. They're all much lighter. And if you look at the Earth, it has too much uranium and iron. And so that's why you posit that there must have been a collision with another small planet, and the Earth captured most of its uranium and iron. And so it's the point of how it's all formed out in the cosmos or something. Forget about that. Just look at the cloud that made the solar system. It had a certain abundance of all those, and the Earth now has more than that.
Yeah, related to the formation of uranium and everything, I read that basically this part of this area within the galaxy has been accumulating heavy elements and everything for 5 billion years before our sun formed. So it's a long time. They think that there was like 10 to 20 supernovas that all contributed to the heavy elements that we have today. Yeah. Okay. Should we break into our discussion groups?
Sure.
Let's go for it. Now we'll get to the spiritual questions. Thank you. Let's thank our speakers one more time.